In my previous video, which I highly recommend you watch before this one, I shared my reply to the Chinese room argument. In short, my argument went like this. Humans categorize experiential abilities based upon a subject's ability to discern relationships. For example, two individuals may have different experiences during a colorblind test, but because they experience equivalent color relationships, certain circles as equivalent or similar in color, while others as unequivalent or different, they are both classified as having full color vision. Searle defined understanding as the ability to experience semantics. With this definition, Searle established understanding as an experiential ability. In other words, a person can understand if they can discern semantic relationships between sentences. Considering a modified Chinese room where numbers represent inputted syntax and outputted semantics, I demonstrated how an English-speaking operator could be classified as partly able to experience Chinese semantics. Because the English operator is a human, they would notice that syntactically unequivalent Chinese sentences, such as "What is your age?" and "How old are you?" were semantically equivalent, according to the Book of Instructions. Because the operator partly experiences semantic relationships in the modified Chinese room, Searle cannot categorize the operator as incapable of understanding, just as he cannot categorize an individual as colorblind solely because they experience the number 12 in the colorblind test differently. With this reply, I only demonstrated how the Chinese room argument, as described by Searle, fails to disprove the possibility of machine-based understanding. I did not, however, make any conclusions about the abilities of machines. In this video, I will share some recent discoveries I have made about one type of machine, the Turing machine. The Turing machine is a hypothetical machine developed in 1936 by the great Alan Turing, a brilliant mathematician, computer scientist, and cryptanalyst. Although mechanically simple, the machine is capable of performing any task a modern-day computer can perform. The machine is made up of two parts, an infinitely long piece of tape and an operator. The tape serves as the memory of the Turing machine. As pictured here, it is divided up into small squares, which are either empty or contain a 1 or a 0. Different arrangements of ones, zeros, and spaces are data, which, as described in the previous video, reveal the relationships between objects. Examples of these relationships include color, volume, speed, size, and etc. The operator is a device that sits atop the tape. It can perform three basic functions. The read function, which temporarily stores the symbol of a single square, the write function, which edits the symbol of a single square, and the move function, which moves the operator to a new square. By combining these three functions, the operator can transform any inputted tape into any outputted tape. Because the tape can serve as any type of data, the Turing machine, with these three functions, can perform anything a modern-day computer can perform. The order in which these functions are executed is defined by the operator's state table, which consists of an onboard container and an instruction manual. The onboard container holds three values: the current symbol, which is acquired through the read function, the state of the operator, and the starting state of the operator. While the current symbol is erased from the state table after the operator moves to another square, the state is not. This allows certain squares on the tape to affect the editing of other squares. The starting tape simply defines the state that the operator will begin with. The instruction manual defines what actions the operator will take based upon the values in the onboard container. For example, when the current symbol and state are both 1, the operator changes the state to 0 and moves right 1 square. The instruction manual, starting state, and tape are provided to the operator by a programmer with some goal in mind. This specific program determines whether the tape has an even or odd number of ones. Each one causes the operator's state to change between 1 and 0, or even and odd. Once an empty square is encountered, the operator records its state on the tape and halts. The programmer can then use this value to determine whether the number of ones is even or not. The Turing machine's ability to read, write, move, follow instructions, store values, and etc. are generally known by those who have studied the machine. I would like to explore an ability that tends to be ignored, possibly because it seems unimportant. This is comparison. In order for the operator to execute the instructions of a programmer, it must be capable of comparing the current state and symbol with those listed on the instruction manual. Comparison reveals the relationships between the current and conditional states and symbols, and as I stated before, humans categorize experiential abilities based upon the ability to discern relationships. What I suggest then is that the Turing machine should be classified as capable of experiencing. Although humans and the Turing machine may have two different experiences about symbols and states, they experience the same data, as they agree upon equivalent and non-equivalent values. But is it possible that in the same way a human and a Turing machine may have different experiences, the two might also experience data differently? This can be easily disproved. It must be first recognized that I am focusing only on the experience of discrete data, which I described in the previous video. This is because the Turing machine has only demonstrated an ability to perceive objects as equivalent or unequivalent, not by level of similarity. Because of this, the transitive property can be used to disprove this notion. I will assume that a Turing machine experiences discrete data differently than I. When observing this triangle, I perceive the bottom squares as equivalent to one another and unequivalent to the top square. This experience does not violate the transitive property. However, the Turing machine's experience does violate the transitive property. To experience discrete data differently, the Turing machine would have to perceive the bottom squares as unequivalent to one another, yet somehow equivalent to the top square. Because this experience is impossible, I suggest that a Turing machine must experience discrete data in the same way as a human. But does this ability apply to other areas of the state table? Just like how the relationships between current and conditional values are experienced, the Turing machine also must experience the relationships between instructions and the actions associated. If the Turing machine did not experience the instruction move right one square and the action of moving right one square as equivalent, it could not be carried out. So I have demonstrated that the Turing machine can experience discrete data in the same way as a human. Does this mean that a Turing machine which simulates the Chinese room or modified Chinese room experiences discrete syntactical data? This is something I cannot prove yet with my current conclusions. However, it is not out of the realm of possibilities. Alan Turing, in creating the Turing machine, unknowingly developed a system which could be classified as capable of experience. But while incredibly powerful, the machine may have the limitations voiced by John Searle, although it may not. The next time you are using a digital device, try to consider yourself in its shoes. Thank you for watching.